Okay, welcome to part 2 of separation of variables. We're just going to jump right in here on example 3. If you missed part 1, you can go back and find that on my webpage. But basically, look in your notes, find example 3, and we want to take this and find the solution that contains the point 2, -5, and then we're also going to state the domain. So dy dx equals x plus 1 over y minus 3, and if I cross multiply, I get y minus 3 dy equals x plus 1 dx. And I'm going to integrate both sides now that the y's are together and the x's are together, and get 1/2 y squared minus 3y equals 1/2 x squared plus x plus c. And I want this to contain the point 2, -5, so I want to make sure that I plug that in for x and for y. So I have 1/2 of 25 plus 15 equals 1/2 of 4 squared is 2 plus 2 plus c. So let's see, this is 12.5 plus 15 is 27.5. Take away 4 is 23.5. So 23.5 equals c. So my equation so far is 1/2 y squared minus 3y equals 1/2 x squared plus x plus 23.5. All right, my next step is going to be to solve for y. And right now I'm really annoyed by all these 1/2, so I'm going to go ahead and multiply both sides of this equation by 2. So I have y squared minus 6y, leave a gap on purpose, equals x squared plus 2x plus 47. I multiplied everything by 2. Okay, why did I leave a gap? Well, because next I need to solve for y. And if I want to get y alone, the only way I can do that is to like solve this quadratic for y, which is going to be easiest if I complete the square. If you were thinking complete the square, congratulations, you get a fake dollar. We'll call it a Bitcoin. There you go. So I have y squared minus 6y, and I need to complete the square. So remember, you're going to add half of this number squared. So -6 divided by 2 is -3. Squared is 9. Can't add 9 to one side without adding 9 to the other, so I shall do so. So this becomes y minus 3 squared equals x squared plus 2x plus 56. And then I'm going to square root both sides. And remember, when I square root both sides, you need to give it a plus or minus. So y minus 3 equals plus or minus the square root of x squared plus 2x plus 56. And then from there, I'm going to have y equals 3 plus or minus the square root of x squared plus 2x plus 56. Well, it says find the solution. How many solutions do I have right now? I have 2, because I have 3 plus this radical and 3 minus this radical. I only want and only need one of them, and I need to pick the solution that includes this point. Well, the y value on this point is negative, and the only way for this equation to yield a negative y value is to use the minus. So I'm going to scribble this out and just put a minus sign. So that is my solution curve, and only that. The next question says find the domain. So the domain of a radical is when the inside is greater than or equal to 0. Well, that's not factorable, so I'm going to quick find the discriminant. I'm going to do b squared minus 4ac. So b squared minus 4ac is going to be negative, which means my discriminant is negative, which means that there is no regular root, which means the roots are imaginary, which means that this parabola is always above the x-axis, which means the stuff inside the radical is always positive, which means the domain is all real numbers. I know that seems a little confusing. How come this negative means the domain is all reals and it doesn't exist? It's because if you have a negative discriminant, it means that this quadratic has no real roots. And if it has no real roots, it always has to be above the x-axis because this opens up. Okay, so my domain is all reals. All right, moving on to the next one. Find the solution here. It contains that point. State the domain. Find another solution passing through there. Okay. So on this one, the first thing I'm going to do before I do anything else is realize that I've told you you can't have pluses or minuses. It needs to be a product or a quotient. Well, fine. I'll make it a product if you say so. Isn't that still a product? Y times x minus 1. All right, so I want you guys to try and do this one on your own. So now that you have it written out this way, I want you to pause the video. I want you to go through and get to the point at least where you solve for plus c. Then unpause it and see if you got the right thing, okay? Try it on your own, solve for c. I'm going to pause and unpause. All right, so hopefully you got a C, and something weird happened, so we're going to go through it together here. So if we look at this, the answer should be that ln absolute value of y equals 1 half x squared minus x plus ln 4 minus 15 halves. If you got that, that's fantastic. Here's how I got there. I divided by y, making this y to the negative 1, and multiplied by dx. The antiderivative y of y to the negative 1 is ln absolute value of y. Antiderivative here is that. I went through, I solved for c. I got this funky looking c, whatever, I don't care. It's still a c. And then I ended up with this. Okay, well, where do I go from here? I've got the c. How do I solve for y? Well, how do I get rid of an ln? I put it back in exponential form. So the absolute value of y is equal to e to the 1 half x squared minus x plus ln 4 minus 15 halves. Well, how do I get rid of absolute value? Well, you get rid of it this way. You think back to here when you were solving for c. When I plugged this 4 in for y, did the absolute value matter? If no, then you can just erase the absolute value entirely. If yes, I'll tell you what to do in a minute. Okay? So if no, you just erase the absolute value entirely, and this is your answer. By the way, an alternate form of this answer, because everybody knows how much I love log laws, would be 1 half x squared minus x minus 15 halves, because technically you have an e to the ln 4 in here, which is 4. This is probably how you'd see it if this were like a multiple choice question. Okay? They also want us to state the domain of this solution. Well, the domain of an exponent is exponents can be positive, negative, they can be whatever they want. So our domain is going to be all real numbers. Okay? Now, the next question asks, what if it passed through 0, negative 6? So if it passed through 0, negative 6, I'm going to do that over here. I would have had ln absolute value of y equals 1 half x squared minus x plus c. I'm pulling that from right here. So then I'd plug 0 and negative 6 in. So I'd have ln absolute value of negative 6 equals 0 minus 0 plus c, which makes c ln 6. So then I'd have ln absolute value of y equals 1 half x squared minus x plus ln 4. Nope, 6. I'm looking at the 4. 6. Then I'd solve for y. Absolute value of y equals 1 half, nope, equals e to the 1 half x squared minus x plus ln 6. Did I use the absolute value? Yes, I did. So if the answer to that question was yes, you have to negate this side. Where'd the 6 come from? Right here. You have to negate this side because technically y needs to be able to be negative, and the only way that's going to happen is if you negate this side. So this would be my solution for that answer. With the domain, my domain still depends on the exponent, and those exponents can be whatever they want. So my domain is all reals again. All right, so we are 9 minutes in here. Fantastic. We've gotten through 2 examples. Turn the page in your notes. That's not it. You can all look. That's my cousin's baby shower invitation. I have no idea why it cut and pasted here, but there you go. So, what am I looking at now? Now I'm even distracted. Okay. Consider this. Find a solution. Find the domain and the range. Use Euler's method. Euler, 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 just in case you forgot how to pronounce it. Use Euler's method with a step size of 0.25 in the initial condition from part A to estimate f of 1. Compare your answer to f of 1 using your function from A. Okay, here's what I want you to do. We've done 4 now, either together or apart. I want you to try to get through A, B, and if you want, even try and get through C. And then we will talk. So tell you what, try to get through A, B, and C on your own. Pause it and come back. I will have them done and go through them relatively quickly. All right, so hopefully you paused and came back. And there's definitely some unique things that go on here, so I'm going to go relatively quickly, but slow enough that you can follow me. So your final answer up top here for A should be that you multiply by e to the 2y, you multiply by dx, you end up with this. The antiderivative of e to the 2y is e to the 2y divided by 2, and this just becomes x cubed plus c. Solve for c. C is 1/2 e to the first. Plug it in. When you need to solve for y, you're going to multiply by 2, then you have e to the 2y equals that other side. To solve for y, you're going to take the ln of both sides, and then you're going to divide both sides by 2, and that is your function. Then we're going to come down here, we're going to talk about domain. Well, the domain of an ln is that the inside has to be positive. So I just took the inside, set it greater than 0, solve for x. And the range of an ln is negative infinity to infinity. The way you can remember that is a regular graph for ln looks like this. It goes from bottom to top. Okay. C is Euler's method. So when we set up Euler's method, you have x, you have y, you have delta y is dy dx times delta x. So in the first row, I have the initial point of 0, 1/2. I plugged it into this expression and got 0. So you add 0 to 0.5, you add 0.25 to x, and you get this row. Plug 0.25 and 0.5 into here, you get that, and so on, and so on, and so on. Your final answer should have been 0.715. And then over here, I took the function that we got, the solution curve. I plugged f of 1 into that and got 0.7757. So Euler's method says by the time you get to 1, y should be at 0.715. And the function said the actual answer is 0.7757. So Euler's, not too far off, like 0.6 off, which isn't terrible. Okay? So that is that. There was a lot of stuff going on here. If I change my zooming here to the entire page, we had to separate the variables to get a solution. We had to find the domain and the range of the solution. And then we had to use Euler's method. All right, this is a little bit more than you'd probably have to do in an AP problem, but maybe not. So it all kind of depends on the year. So hopefully if that all made a lot of sense for you guys, if we come back to this last one, we have a function. They want you to do a bunch of things to it. Tell you what, try this one again on your own. When you come back, I'll go over it so I can shorten up this video a little bit, and then we'll call it quits. So pause, pause, pause. You should really try this on your own. Pause, pause, pause. Very quickly, if you haven't paused yet, this means take the derivative. You're going to do that implicitly. This you're going to separate variables. This you're going to do Euler's method. So implicit differentiation that kind of comes out of left field. Separation of variables. Regular function. Okay, so for this one, when we take the derivative for a, they just want the second derivative. They gave you the first derivative. Since your derivative has x's and y's, you're going to need to use implicit differentiation. So I take d dx of both sides, which makes this a d2y over dx squared, and makes this a product rule. The first times the derivative of the second, plus the second times the derivative of the first. Well, it has a dy dx in it, so I just substituted the dy dx in for dy dx and wrote it like that. Then they told us to evaluate that at 3/1/4, so I plugged 3's in for all the x's and 1/4 in for all the y's, and got -1/8. Part B is what we've been working on, separate the variables. So you can kind of see it a little bit ahead on the right-hand side here. So we start with this. We separate the variables and we get y to the negative 2 and 6 minus 2x. When we integrate, that becomes negative y to the negative 1 and 6x minus x squared. I plugged in the initial values to solve for c, which is negative 13. Substitute, multiply both sides by the negative 1, raise both sides to the negative 1 power. And there's your solution. And then last but not least, they wanted me to use Euler's method. So they said use Euler's method, start with 3 comma 1/4, and estimate 2.7. Well, if I start at 3 and I want to go back to 2.7, my delta x is negative 0.1. So when I go through and I do the delta y, it's the derivative times negative 0.1. And I just did it a line at a time. 0.246. Ta-da! And there's a grouchy looking e-card, and let's see, we need a joke for today. A Valentine's joke. What did the farmer give his wife for Valentine's Day? Hogs and kisses. Ha ha ha. Okay, I'm done. Lots and lots of math. Everybody loves math, and there were logarithms, so I'm pretty happy about today. I hope you enjoyed this as much as I did. We will talk later. Bye.